Through laser interferometry, the lathe's geometric errors were mapped and placed into the software of the turning center controller. Alkan Donmez, an engineer who did his PhD research at NBS, discusses the achievements of geometric and thermal error correction.
Another major achievement was to eliminate the warm-up time of the machine tool. Regularly, the machine tools require long time periods before they reach the thermal equilibrium, like, for example, about 8 to 10 hours. With error correction system implemented on this machine, we were able to start the machine in the morning, a cold machine, and make the parts without any concern for the machine warm-up cycles. And with the thermal compensation that we applied to the machine is capable of getting the same accuracy on the parts while it's cold or while it's hot at the end of the 10 hours working.
During machining, the actual length of the tool changes due to wear, affecting precision of the machined part. At a preset interval, the tool position is measured and compared with its original position. The offset is calculated and compensations are made. Automatic tool setting can now achieve 50 times the accuracy of preset tooling, dramatically decreasing scrapped parts. This turning workstation reached a significant milestone when it recently ran unattended for 25 consecutive hours without failure. Computer scientists are studying the organization of data and data formats to help automate the analysis and indexing of part designs. Instead of warehousing parts, industry will be warehousing data. Group Technology clusters similar attributes of parts and the problems faced in their manufacture.
Could you bring up the database definition for parts here? Let's look at the structure of the surfaces.
Generic solutions to those group problems are developed through experience and are then modified to fit the particular problems. These will act as guidelines to plan for the manufacturing process. Group Technology will be playing an important role in developing what is called process plans.
Test parts such as this one manufactured at the vertical machining workstation and similar parts manufactured by the electronics industry of the same family are of the variety that we are currently planning at the process planning workstation. The process planning system provides us with the capability to specify the resources and the procedure or steps necessary to make a part. Down at the machine tool level in the process planning system, we specify a part in terms of features. Some of the features the system supports are O-ring grooves, pockets, and through holes. From our feature description of the part, we're capable of automatically generating the numerical control code that is used to run the machining center. Our major goals of this project are to develop standard data structures for process planning and to improve the productivity of the process engineer. At the vertical workstation, we are illustrating the link between process planning and control software. We describe the part to the system in terms of a process plan. We specify individual features, and that features are automatically used to generate numerical control code to run the machine tool on the shop floor. What I'd like to show you on the screen here is how I change the description of the part. I'll change the dimensions on a pocket, add a hole to the part, and then I will release that process plan to the vertical workstation controller to execute on the floor. Now, I don't mean to imply that the machinist would be perhaps changing the design of the part on the floor. What we're trying to show here is the flexibility and then the interfaces between the different systems. Let me show you how easy it is now to change the part design. We have a groove here that's illustrated that runs the length of the part. I'm going to change the dimensions of that so that the groove is shorter. Okay, and now I'm telling the system to make the part. I've entered the process plan number, and if you look out here, you'll see a part has been injected at the first part feeder. The robot is going to move into position, grab the part, and take it over to the fixture. Okay, it's grasping the part now. We'll place it in the fixture, and the fixture will close on the part.
All the equipment in this station is integrated into a single operational unit in a standalone mode. Later, it will be tied into the overall AMRF control, communication, and database system. An extraordinary array of parts, generally taking days and often weeks to design and produce, are being made here in minutes. At the cleaning and deburring workstation, AMRF engineers are conducting research on cooperative action by 2 robots. In this exercise, the objective is for the pin, representing a deburring tool, to follow the contour of a finished part, maintaining constant force. The computer screen demonstrates the system's sensory interactive ability to bring the force back to the correct range and to detect a part whose characteristics are unacceptable. Until we have learned enough to build a factory with true deterministic metrology, automated inspection will play a major role in achieving quality. This workstation is inspecting parts machined in the AMRF for dimensional accuracy. Dimensions found to be out of specification are flagged. An optical scattering system provides surface finish inspection. By the end of 1986, the inspection workstation will be integrated into the overall AMRF system. In later stages of development, inspection results will be fed back to the database for process control, for go, no-go decisions on acceptance of parts, and for analysis in revising the rules used in expert planning systems. Research continues at the AMRF through cooperative programs with industry, academia, and other government agencies. By focusing its efforts on interface standards, in-process measurement, and issues of factory system architecture, the AMRF is supporting the nation's requirements for standards in automated manufacturing.